By now we all should be quite comfortable using functions. But there are situations in which functions just don't provide us enough abstraction. A solution to this is to introduce the custom types, otherwise known as classes. Let me illustrate what I'm talking about by an example. Imagine that we want to write a small game about a cat that roams around the world looking for adventures. The cat starts off as pretty grumpy and gets its happiness up by doing some fun mischief, like throwing a vase from a table. It's not all fun though, and some actions are dangerous, and sometimes, rarely, the cat will lose one of its 9 lives. We win the game once the cat happiness reaches 100% or it has explored every corner of the world. If our cat reaches 0 lives, we lose the game. Sounds good? So how do we model this, taking into account everything that we know until now? And before we directly jump into coding this, we would like to model our world and our cat using some variables. For simplicity, we will assume a line-like world, which we then can represent as a vector of fun and dangerous events randomly generated for each game. The cat then can be represented by its position in the world, number of lives, and happiness. The coordinate increases and the cat finds more events, which updates the cat's parameter. I suggest you to pause the video here and to try to model this game on your own. How would you write this using just the functions? One way or another, we will probably come up with something like this. We will have a couple of includes, we'll have a couple of constants, and we will have to enumerate the events that the cat can encounter, like the no event, the fun and dangerous events, as well as the event for the world being completely explored. And now we get to the point where we have to model our game, and by modeling the game here I mean to write out the functions that we will use here. The functions that I came up with are the generateWorld function that just returns our new world, the function moveCat that moves a cat or increments its position, a function to find the next adventure for the cat, it needs the world and the current cat position and gives us the event, and 2 more functions to update the lives of the cat and to update its happiness. Let's see how we can use these functions to actually write out the code for the game. We write it in the main function, we first generate the world, we initialize the position, the life counter and the happiness of the cat, and then we have our main game loop, we write it with while true, and we update the cat position, we find the next event, we check if the world is fully explored, then we win and stop the loop. If not, we go further and we update the lives counter of the cat, and if this lives counter is below 1, unfortunately we lose and we have to break the loop again. But if we go further, then we have to update the cat happiness, and if this happiness is too high, then we won, and because the cat is happy, so we have to break again, and we repeat this until one of these conditions is met. Note how I did not implement the functions and just declared them. It's usually enough when designing something to get a feeling for the resulting system. We can fill the implementation once we're happy with the overall design. Once we actually implement all the functions, the code works and it's kind of fun to play with. For example, we could print all the events that the cat encounters while it explores the world. But we quickly start seeing the limitations of this approach once we try to extend it, for example, if we have more than one cat. We would now need to store the cat properties in vectors. So we would have a vector for the happiness, a vector for the life counts, and the vector for the positions of all of our cats. Now think about this, you will have multiple cats, multiple vectors, and now you have to traverse those vectors in sync, which opens us up to this off by 1 error that we discussed before in the vectors lecture. This is not very neat, we can probably do better. So wouldn't it be nice if there was a way to capture our game setup in a more abstract way, so that the code is more readable and the logic is clearer? And of course there is such a way, otherwise you would not be watching this lecture over here. And the solution to our problem involves custom types. Before we go into the mechanics of the custom types, let's first try to understand what they do on a more abstract level. And we will use our example again, so here our idea will be to bundle the data and the methods to process these data into our custom cat and world types. Let's rewrite the code a little bit to use our custom cat and world types. I will not write them out just now and will hide them behind this magical comment over here, but let's see how they change the main function. So instead of defining all of the variables for the cat and the world as we did before, we now just create 2 variables, the world and the cat. And all of the functions basically now work on the cat. So to find the next adventure, we call it on an object of a cat. So we ask a cat to find its next adventure and we give it a world to look for events in it. The conditions are exactly the same. We still have to update the lives and the happiness if we haven't explored the whole world. The only difference is that now we can actually check our conditions in a different way. We can ask the cat if it's alive or if it's happy, instead of just ad hoc writing the functions out. Or if we think more about how we interact with our cat, the update lives and update happiness functions look more like an implementation detail of the cat itself, so we could hide them into our already existing find next adventure function, further simplifying the cat interface. Which means that we can remove these two functions over here, making our code even shorter. Now this looks much better than before. The new code is more readable for humans and is going to be easier to maintain. This is of course just one way to design such a game. If you have the time, do think about the alternative ways of how this could be achieved. And once you write it, think how to extend these systems to more than one cat. Maybe even more than two. Okay, now that we know at least a little bit about what do we need the custom types for, let's talk about how do we write them. First of all, let's get the language out of the way. Here, the cat with a capital C is called a class or a user-defined type. The grumpy and initialized cat and the cute initialized cat are variables of type cat. They're also often called instances or objects of type cat. Note that in this example, the grumpy uninitialized cat might remain uninitialized, thus the name, which might lead to undefined behavior. Unless you have a good reason for it, always initialize variables also of your custom types. In this course, we will name the custom types that we write in camel case and the variables of those types in snake case, just like any other variables that we've seen before. A custom type usually consists of two things: the data that it holds and the methods that work on these data. And these two things together are usually called encapsulation, which is just a fancy word that we use to describe that we put all the data that belongs together in one place and then bundle the methods that work on these data along with them. First of all, there are two C++ keywords that indicate to the compiler that we are defining our custom types. It's a class and the struct. We're going to use class for now and talk about struct at the end of this lecture. In the beginning of this lecture, we kinda already have designed our cat methods without ever thinking of the data that the cat has to store. In other words, what a class does is more important than how it does it. The class methods form its public interface, answering the what question, while the data the class holds answers the how question and is just an implementation detail. And that's why the methods come always before the data. If we change the data of our class without changing its public interface, nobody should ever notice. Armed with this, let's fully implement our cat class. We define a class by typing the word class, its name, and brackets with a semicolon in the end. And classes have so-called access modifiers, the public and private. Well, technically there is also the protected access modifier, but we will talk about it later in the coming videos. Everything under public is a public interface and can be accessed from the outside. For example, the isAlive function can be accessed from the outside, because we want the user to be able to check if the cat is alive. And everything under private is an implementation detail and is only accessible from within the class methods. For example, the function update happiness should not be available to the user, as the cat decides if it wants to be happy on its own, without the user input. This is a fundamental principle behind encapsulation. The data that is stored within our class is only available within the methods of our class, so that every instance of such a class has full control over its data. Actually, let's write a small main function and compile this code to illustrate access modifiers in action. We write the small main function, we create a cat object and we call cat isAlive on it. Let's try to compile that. Note that we use the -c flag because we don't have the implementation of the functions, so we don't need a linker to kick in. We just want to compile it. Okay, and it compiles. Now we can add the update happiness function and suddenly it stops compiling. And you can see that the error is that we are calling a private function and this is not allowed. Also note that we should always start a class with public and the private part always follows later. The reason being is that we read the code from top to bottom, and when we start reading the code for the class, we want to read the public interface first because that's how we interact with the class, and we usually don't really care about the implementation details, which are stacked away into the private part. One more thing I wanted to draw your attention to is this const at the end of isAlive. We haven't seen something like this before. Essentially, this means that these functions guarantee that the object on which they are called is not going to be changed. And this works by basically assuming that all of the data inside of the object is const while in the scope of such a function. However, this has the following caveat. If the method is not marked as const, the compiler basically assumes that in order to function, it needs to change the object. So if you try to call a non-const method on a const object, it won't compile. Let's illustrate how it works. First, let's add a dummy non-const function to our cat class and verify that we're able to compile the code as is using our already existing main function. Now, let's make our cat object const for a second and try to call const and non-const functions on it. This results in an error and tells us exactly what we did wrong here. Note that this error can be different for different compilers. Now, with this out of the way, we can quickly finalize our public interface. And the only thing to do after that will be to fill in the actual code. Okay, the first two functions are easy. They just return a boolean, but they touch upon a cat internal data, which we always put in the private part of the class. Data should always be an implementation detail of a class and never a public interface. We name these variables in snake case with a trailing underscore, just to make sure that we see which variables we're working with within the method. And just as with any other variables, we don't want to leave them uninitialized. Just like we discussed in one of the first lectures of this course. This helps us avoid hard to debug undefined behavior. Now we get to the most interesting function of our class, the findNextAdventure function, as it has most of the logic. We'll first outline this logic with calls to some functions that we can then fill in with the actual implementation. These functions will all live in the private area as they should only be used from within the class methods. Feel free to pause at any time to look into the implementation more precisely, but once these functions have the actual code in them, we have fully implemented our cat class. Okay, I nearly forgot to talk about structs, but we'll do it now. Structs are not that much different from classes. In fact, they're exactly as classes, with just one tiny difference. And this one tiny difference is that if you leave a class without any access modifiers, everything will be private. But if you leave a struct without access modifiers, everything will be public. Other than that, they're exactly the same, and you can verify this by changing the class cat into a struct cat. We have to be careful with this though, because having everything as public breaks encapsulation. Now suddenly everybody can change anything within our class, and that means that we don't control our data anymore. So the rule of thumb here is to only use struct if you are not planning to have any methods, or for data-only structures, or data-only types. But if you are planning to have at least one method of your struct, it should be a class. Okay, now we know what custom types are, why we care about them, and how to implement them. And this is an important topic because a lot of modern C++ is based on solid understanding of how to write our own custom types. And in the following lectures, we're going to look into more aspects, into more details of how to implement these types and what quirks to expect there. Thanks for watching as always, and if you like what I do, then tell your friends, and you can subscribe to my channel over here or watch the next video over there. Thanks and bye!